Alright, this is a problem back from our Halliday and Resnick book. Thought it was a good one to look at. The elevator problems are often confusing to some, and I totally get it. What we have is a mass, we can say our combined mass, and our feet are glued to the floor, is 500 kilograms, and it's initially going down with some initial velocity of 4 meters per second. We'll call that a -4. We'll see that the minus sign is going to vanish. But the supporting cable holding this thing up here slips, and it starts to accelerate with a magnitude of the constant g over 5, or a fifth of g. The first thing it wants to ask is, after it falls 12 meters, what is the work done by gravity? Well, first of all, we should see that the displacement can call this delta y, is actually in the same direction as the weight. So we can say that the angle between the two of these is 0 degrees. Alright, using our work formula, we can say the work done by gravity is then equal to the force of gravity, mg, and it's traveling through some, mg cosine theta, and it's traveling through some displacement delta y. Cosine of theta is 0, and in other words, cosine of theta is 1. So we just reduce this down to mg delta y. Okay, now the work is positive in this case. And why? Our work definition is F times the displacement. If they're in the same direction, it's positive work. So if I was lifting the elevator, this would be negative. But since the elevator is going down, we end up with a positive. And what do we get? 500 kilograms times 9.81 meters per second squared. And our displacement is what? 12 meters. And cranking the handle, we end up with 59 kilojoules. So this actually came out to be 5.88 times 10 to the 4th joules. You need to know how to put that into kilojoules for sure. Energy is one of those things where a lot of the stuff has large magnitudes. This has a magnitude of an order of magnitude of 4, so it's pretty big. We can write it more simply in the kilojoule fashion. Okay, so that's part A done. The work done by gravity, pulling it down, is 59 kilojoules. Now they say during that 12-meter fall, so it still fell 12 meters, what is the work from the tension of the cable? The tension's pulling upwards, so if we have mg going down, our tension is going upwards. So let's use that and do Newton's second law. And say we have a tension pointed up and mg going down, and that's going to equal the mass times the acceleration of the whole system, or the whole elevator and the person inside. We can arrange this and solve for tension. We get mg plus ma, or tension is equal to mass times a plus g. Now, they told us that it falls with an acceleration equal to g over 5. Let's go ahead and stick that right there. So I get a tension equal to the mass times, and it's going downward, so it's a minus g over 5, and a plus g, and it goes through some distance d. I like writing it this way. There's some angle between the force and the displacement we can call phi, and it goes through some distance delta y, right, the 12 meters. Now what's the angle here? We have a tension pulling up. That's our force, but our displacement, delta y, is in the opposite direction. So phi is equal to 180 degrees. Simplifying this, we get the tension equal to, we can combine this to be 4/5 g. 1g minus 1/5 g gets us 4/5 g. And then, let's actually crank the number. We have 500 kilograms. We have g as 9.81 meters per second squared. And it goes through a cosine of 180 degrees at a distance of 12 meters. Okay, cosine of 180 degrees, I would have to unit circle it, 180. Over here the cosine value is 1. Over here it would be -1. So it's going to change the sign on all of this. So we're going to get a negative 47 kilojoules. Negative sign because the force and the displacement, delta y, were in opposite direction or opposite sense. Alright, part C says, what is the net work done on the cab? Net work just means we add it all up. So we can say work net. Well, we had some from the tension right here, so the work from the tension plus the work from gravity. We have minus 47 kilojoules from the tension, and what was our 59 kilojoules from gravity. The net work is equal to 12 kilojoules. Alright, and the last part is going to get us to use the principle of work and energy. So it's asking, what is the cab's kinetic energy at, let me write that, kinetic energy at the end of the 12-meter fall. So at 12 meters. After it's fallen 12 meters, what's its kinetic energy? Kinetic energy is equal to 1/2 mv squared. So we'll hold on to that for a second. And let's also use the fact that work is equal to the change in kinetic energy. Let's break this up some more. That means 1/2 mv final squared minus 1/2 mv initial squared. Alright, they want to know what the final kinetic energy is. That's this. So we can actually rearrange for it and solve for this and say, okay, the kinetic energy final is going to be equal to the work plus whatever its initial kinetic energy was. This is its initial kinetic energy. Remember, it was going 4 meters per second before the cable started unspooling. Well, we have the work, we have the mass, and we have the velocity. So we can figure out what the kinetic energy is in its final state. It's going to be that 12 kilojoules. Sorry, just looking at something real quick. And then we have our kinetic energy term, 1/2 times the mass, which was 500 kilograms. And it was moving at a speed of 4 meters per second. It doesn't matter which direction because we're about to square it. Kinetic energy is kinetic energy. It doesn't matter what direction you're going in, it's just the speed. Okay, so if you did have a velocity vector with I and j components, you'd want to know the magnitude to put it into the kinetic energy formula. Okay, from this we get a final kinetic energy equal to 16 kilojoules. That's great and all, but that doesn't really tell us much. It'd be more interesting to know how fast it's going, in my opinion. How fast after 12 meters? Well, if the kinetic energy in its final state is 16 kilojoules, we can just solve this. We can say 1/2 mv final squared is equal to 16 kilojoules, and solve this for v final. It's going to equal that 16 kilojoules divided by the mass times 2, and then we take the square root. That's more interesting information than this, in my opinion. So from that problem, we could figure out how fast it is going after it fell a distance of 12 meters after work was being done. It had some initial kinetic energy, 1/2 mv squared, and it now has some new kinetic energy and some new velocity, which is directly related, or related as a square, right? Kinetic energy is proportional to the square of the velocity.